One tool that's used really quite broadly in the developer community, in programmers, in web developers and web application developers, anytime there's a team of people working together on a collection of software files, whether that's a web application or something more detailed like C or Java, are software configuration management tools such as Git. So in this lecture, what I'd like to do is give a high-level overview of the software Git and how it interacts with GitHub to try and orient you to some practices that are commonly used in the industry for managing teams of people with the software that they're developing. So this is Intro to Git, and I'm Professor Don Patterson. At a high level, what we need to remember is that software consists of many files, often deep directories of files that have to all be coordinating with each other in order to make something happen, a website render or a program to run. The other thing to remember is that creating software is a very collaborative activity. Unlike the reputation that programming often enjoys, unfortunately, programming is not a solitary activity that's done somewhere off in the basement in some dark room. It's done by teams of people that are working together in very difficult and complex technical environments with a lot of pressure and time deadlines as well, time pressure. And as you're working on these projects, many people have to change these files simultaneously. And as you have many people working on these digital objects at the same time, it can become hairy and chaotic to make sure that all the files are working together, because they all do have to work together for your projects to work. So Git is a software tool that helps to manage these changes and tamp down on some of the chaos that can result from these environments. Git is a program that is an example of a whole class of software solutions that's called software configuration management, or sometimes also called source code management, or SCM. This is a generic term, and it refers to a software package that has the ability to manage multiple versions of a document, or more usually a collection of documents, trying to keep them all together and reasonable and understandable. Here's an example of GitHub. GitHub is an example of a cloud-based implementation of Git with some additional features that have been added on as well. In this class, we have worked with GitHub already, and we've generated a collection of files. Here's an example of the files that are currently in my demo directory. And you can see that even with a very straightforward, simple solo project, I'm already starting to develop 5 different files that are now changing at different times, in different ways, and those files depend on each other. My HTML files are referencing my CSS files, and my CSS files are referencing other things on the internet as well. So I'm starting to have these interdependencies between these files, and I need to make sure that they're all coherent and consistent. This is a snapshot of the files at one moment in time. Kind of think of that as maybe a horizontal snapshot. But you can also look at this repository of files in a vertical snapshot. And in the vertical snapshot, what you can see is a history of the way in which these files have changed. Each time a change has been made, we call this a commit. A commit is a collection of changes that are being made at one time, and you're kind of wrapping them up and stamping them and saying, here's a change to my collection of files that's integral and atomic, and I want to take place all at once. So you can see I have 1, 2, 3, 4, 5, 6, 7 different commits in this project so far. A handful of them are creating files for the first time, and then I have some updates as well. That creates a timeline. A lot of programs actually have built-in configuration management as part of the application. These aren't software programs, so we wouldn't call them software configuration management, but configuration management is probably fair. A very simple example is Microsoft Word. Microsoft Word will make backup copies or autosave your document in case something happens to Microsoft Word in which it crashes for some reason, however frequent. Because it has the backup copies and the autosave feature, when you restart Microsoft Word, it can look to see if you have any backup copies, a history of changes to a file that you've made, and it can ask you if you want to use the most recent uncorrupted version instead of maybe the last one that was working when the file collapsed. This is a very simple example of configuration management. You just keep track of the previous version of your document in history. And it's usually only just one document at a time. So that's a straightforward example. Maybe a little bit more complex example is the Mac operating system's time machine. Time machine is a way in which backups are stored in the Mac environment, and it is snapshots of all of the files in your hard drive as they change over time. So the horizontal slices in Time Machine, which we would each call commits in software, but in Time Machine they're dates. So when you take a snapshot of all of your files, you get a horizontal slice, and then as you move forward in time, you take another slice. And between each moment in time, all the files on your hard drive progress forward into time, and some subset of them have changed. But you get all of the files that have changed at any given moment as you move through each snapshot in time. Many programs on Mac have revision management built into them as well, which is the same thing as what Microsoft Word does with backup copies, but the built-in Mac functionality keeps track of many, many, many revisions of a particular document, not just the most recent one, and that's likely tied into the time machine mechanism also. On the web, you may not have looked into the details of it, but Wikipedia also has a history of changes made to any given document. So if you're interested, you can look at the changes that have been made to any Wikipedia entry, and you can see over time all the changes that have been made to that one single document. So while the Wikipedia changes don't reference changes to multiple documents the way Time Machine does, it's more along the lines of what Microsoft Word does, in which it's keeping track of one document changes over time. What's different about the Wikipedia case is that it shows multiple different people making changes to one particular document. And in that way, it resembles more the way software code gets changed. Finally, another example is Google Docs. If you go to a Google Docs, just like Wikipedia, Google Docs has a revision history of a particular document, so that if you're co-editing a document with other people, you can see over time the changes that have been made, and you can go back in time and undo changes that have been made if you don't want them, or you can look to see what contributions individual people made. So let's look at what that looks like in the user interface. So here's Google Drive. It's an example of a paper that I edited with a whole bunch of people. And you can see over on the right the revision history of this document. And you can see that there were lots of changes over the point at which we were writing this paper. And if you click on each particular entry on the right, you can see the changes that were made in that particular commit. Each one of those bars represents a commit, or a collection of changes that were snapshotted at one moment in time. If you look at the way Time Machine works, this is what Time Machine looks like when you use it. This is a photograph of my screen because it's difficult to screenshot Time Machine when it's actually working. So here's a slide deck talking about a slide deck in which I was also talking about Git. And you can see that as those windows go off into the distance, that's Google's visual graphic design for representing the previous snapshots that have been made to all of the files in my hard drive at one time. So each one of those windows going back into time represents a snapshot or a commit of all of the files on my hard drive, so that as I move back, I can go back in time for every file on that particular date. The built-in example, for example, on Keynote is under the File menu, and if you look at that, it gives the user the opportunity to revert to a previous version. There are a couple convenient ones, for example, the last saved version or the last open version, or you can browse all versions and you'll go into an interface that looks a lot like Time Machine. So all of these are examples of built-in change management systems that help to keep track of how documents evolve over time and their trajectory of changes. Why might you want to do this? Well, we've seen examples that one of the big motivations for doing it within a software package is for backups, to restore against disaster. You lose power, you drop your glass of water on your computer and wipe things out. It would be nice to have a backup, and change management software automatically keeps backups for you as you take these snapshots or commits. In addition to that, you might like something like a robust backup. So you might like to know that the software at each given stage hasn't been vandalized or changed in any particular way. And so you would like to keep track of the connection between each revision along the way to make sure that someone didn't insert some kind of change that you didn't expect. Maybe a really large document on the web, you want to make sure that someone didn't edit it that wasn't supposed to. Of course, we're not interested in just one document, we're interested in collections of documents. And that's because files have dependencies between them when you start looking at projects. What do I mean when I say dependency? Well, in our example, we have seen an HTML file that links to an external cascading style sheet. That external style sheet is a separate file. So as soon as you make that change in your HTML, so that your HTML now references your external style sheet, you've now changed two files, and both of those changes have to be snapshotted at the same time for your application to work. You can't just update your HTML because it references a file that maybe doesn't exist in your snapshot. If you update just your external style sheet, it's not referenced anywhere, so there's no point in keeping a track of it. It only makes sense to snapshot both of those files or commit both of those files at the same time because there's dependencies between them. Not just HTML and CSS, but you can also have various kinds of configuration files. The way in which you run your program might require a configuration file, and that has to be changed at the same time at which you change something else. So those are some of the motivations for it. Software is a specific case. It has its own challenges with regard to change management, and that refers to the fact that you've often got multiple versions of your software operating or available in the wild at the same time. So you might have the version of your web application that's currently released and running on the web. You might have a different version that's not publicly available, but that the developers are working on for the next release. You might have a customized version that is being run for a specific client, maybe one that has that's a white label software that has logos for the clients. The client's logos have replaced your logos on the application. Or maybe you have a version that's been forked, or you're trying out a completely different conceptual direction or a set of features that you're not sure you actually want in your release. And so now you have a separate copy of all of your files to view that. All of these are cases that software management systems can handle quite well, in particular for the case of software. If you wanted to, you could keep track of a complete set of all of your files every time you made a change. So when it's time to make a change, you copy the entire subdirectory of all of your files into a new subdirectory, and you only edited those. And then when you want to make a new change, you'd copy all of those into a new directory. Very quickly, you would have a proliferation of directories that duplicated tons and tons of files, even if all you wanted to do was to make changes to a small set within them. So this means that if you wanted to keep track of versions this way, you wouldn't need any extra support, but you'd be keeping nearly identical copies in all these different directories at the same time. And it would require a lot of administration and a lot of discipline to make sure that you were keeping track of what each one of these directories meant, that you were archiving them properly and organizing them properly. You would also need very careful permission management to make sure that the people that were allowed to read and write to different locations were able to. And in some cases, you need to be careful that your intellectual property is being appropriately managed along the way as well, so that you don't have someone put intellectual property into your code base, for example, including an unlicensed font, without noticing it. So what source code management programs do that work with many files is they solve some of these problems. They enable you to make multiple versions that don't duplicate files, but that rely on the same parent files. And they support checking in, keeping track of who changed files and what changed along the way. They automate the management of software. Some examples of this, some of the tools that are used, historical ones are CI and CVS, current versioning system, Subversion, which is abbreviated SVN, Bitkeeper and Mercurial are examples of competitors with Git. Git is an open source version that was developed by the Linux community. And then GitHub is a web-based service that uses Git in order to help create locations on the internet where software can be shared. A big thing that what we're trying to do here is avoid something called dependency hell. And that's a situation in which you have libraries that your software uses, so other people's software that you're including in your software environment. And when you release your new version of software, oftentimes you require a specific version of a library as well. And if you don't update both of those things at the same time, then you can have your software break. And because you are releasing new versions of your software all the time, and the library is releasing versions of the software at all the same time, if you don't have a consistent way of making sure that those are moving in lockstep, you can release software that's going to be broken. So without a consistent way of understanding how versions change, you might have to you might have to keep a completely separate version of each library and everything that depends on it. All right, so there's something that is used a lot in programming environments that you've probably seen, but maybe have never had described to you, which is called semantic versioning. And this is a numbering scheme for just linear changes that happen to software code. So it's a subset of what Git supports. And so what you do is you see this in changes to software. So given a version number that's structured as a major number, a period, a minor number, a period, and a patch, you make increments to those numbers depending on how big of a change has been made to your software. So you update your major version when you make changes to your software that previous versions of your software can't interact with. So like maybe you have what would be a good example? Maybe you have a version of an application on your phone and it connects to a server, and when you make changes to the application on your phone, and when you do that, it can no longer talk to the older version of the server. And so you might need to update your major version. A minor version is usually a version that adds features but allows you to maintain backward compatibility. And a patch upgrade means that you're usually addressing stability and security concerns and bug fixes within your software. So what you do is you see this when you download software. You'll see something like download Python 3.5.2 or 2.7.12. And these aren't numbers in the sense of decimal numbers. What they are is they're three individual numbers that each increase in a hierarchical way. So the next version after 2.7.12 might be 3.0.0, might be 2.8.0, or might be 2.7.13, depending on the kind of change that's being made. If you use Perl, Perl has lots of versions as well that you can download. Here's a bunch of examples of them, and you can see that they are increasing according to the scheme. Perl 5.10.1 increasing to 5.12.5. The only thing I would caution you against is that you have to be careful that you understand that these aren't numbers, they aren't decimal numbers. There are three separate numbers that are each increasing in a hierarchical way. The number on the left is the major, in the middle, and then the patch is on the right. So now you can think of this as a linear progression of releases of software. So along the bottom of this diagram is a bunch of snapshots that represent commits within software. So 4.0.0 represents the name of a particular snapshot of your software. So the name of that snapshot actually references a complete moment in time for your entire collection of files that are present within your repository. You might make changes to that repository, and later on, you'll name another snapshot, 4.0.1. And you'll continue naming those snapshots until you get to a point at which you're going to commit changes to your whole collection of files that are so different that it's no longer going to work with previous versions. And so rather than calling that next release 4.1.3, you go ahead and upgrade your version number to 5.0.0. So as your changes progress through time, and as you make changes to your collection of files, you'll name particular snapshots with these numerical numbers in order to communicate the current version of how it's happening. Now in this diagram, it's actually hiding some changes because each of those arrows may internally have lots of changes that are happening before these big naming events. So these major minor patching events are big naming events that happen for the public release of software. But internally, there are a lot of changes that are happening in between these major events, and software change management software helps those internal changes as well. This versioning scheme is great for releases, but it's less helpful for the active development of software. So let me throw out some terms that we use specifically when we're dealing with Git. We use the term repository to refer to a location where files and their history are kept together. So GitHub has a repository of particular code bases. You might have a copy of that repository on your local machine as well. Other people can also have repositories of that same software project. You can check out software. Check out means to take out of the repository a particular snapshot at a moment in time and begin working on the files from there. Working copy means the files that you're working on after having been checked out, having a set of files checked out from your repository. Checking in files or committing files means to take all the changes that you made to your working copy and then submit them to your repository and take a snapshot, a moment in time. Just like when we saw Time Machine, we went forward and we took another snapshot. Each one of those snapshots represents committing files to a marker in history over time. The thing that's complicated about software is we might actually branch. And what that means is that maybe you will check out some software and I will check out software at the same time, and we will make changes that start to diverge from one another. So while both of our sets of files originated with a common ancestor, they're now beginning to diverge going forward into the future. Merging is the process of taking those two divergent sets of files and bringing them back together into one consistent snapshot, one consistent commit. A conflict occurs when you try and merge files together, but you can't because the changes that have been made are exclusive. So for example, if I make a change in my HTML file that references one web font, and you make the same change in the HTML file that references a different web font, when you try and merge those, there's a conflict because we've both made changes that can't be resolved easily. So we have to get together and manually resolve that. So resolving means to fix the conflicts before you can merge. So here's an example conceptually of how these different processes might occur. So let's start by thinking about the yellow line. And what we're looking at is a timeline of snapshots going forward. Each one of these boxes represents a whole collection of files in a directory on your hard drive. And let's say we have that collection of files that exists at a moment in time, and we call that the first position, or 1. And the yellow line represents our official copy, or what we'll call our trunk. This is the copy that ends up getting released to the world when we're comfortable with the way that the software is developing. So as time moves on, the files within the trunk change. As we go from 1 to 4 to 9, some subset of the files in the collection of files gets changed in each set, 1, 4, and 9. Now we might start with the files as they existed at point 1, and we might decide that we're going to branch. And that means that we're now going to start editing the files, and it's going to be edited possibly in parallel with other people. So we'll branch, we'll edit some of those files, and we'll commit, and that commit becomes commit number 2. Then we'll make some other edits to the file, and we'll commit again, and that will now be commit number 3. Well, now we like those commits. We like the changes that we made, and we said, oh yeah, that's something that we need to release to the public, so we need to merge that back in to our trunk. And so the process of taking our branch at stage 3 and then merging it into the trunk is stage 4. That's called a merge. Hopefully that happens cleanly. Once we merge in the changes we made, let's release that. And what we're going to do is we're going to tag all of the files that were present at moment 4, and we're going to give it a version number, a major number, a minor number, and a patch number. And we're going to let the rest of the world have access to the files in T1 in some way. Maybe put it up on the website. Meanwhile, while the files in T1 are running on our website, we're going to continue development from the files as they existed at time 4. So at time 4, we're on our trunk, we're going to branch again. Now we're going to branch into another snapshot at time 5. And now you can see that the code that's running on our website, represented by T1, the files that are being delivered to people using our website, are now diverged from the files that we're working on in snapshot 5. They both have a common origin at a moment in time of snapshot 4, commit 4, but now they're starting to diverge. So we like 6 branches, but actually 5 is going to branch and become one set 6, and we're going to have another developer that's going to start working off of a common ancestor of 5, and that's going to become 8. But our branch from 5 to 6 continues. We make another commit, we make some changes, we commit, that becomes commit 7, and we like that also, so we're going to add that into our mainline trunk. We'll merge that in, and that'll become commit 9. We'll say, yeah, commit 9 is good, so let's send that out to the world. So we update our web application, and we create a new version number. Maybe it's 5.1.2. I forget what I said T1 was. T2 now goes out to the public, and we see T2 is based on 9. Now, meanwhile, there was another branch. That was a release of T2. Meanwhile, there was another branch over on 5, and when 5 branched to 8, there's a special name for that branch, and that branch is called a fork. And the only difference between a fork and a branch is that a fork never gets merged back into the trunk. And so it's a bit like a species diverging in an evolutionary context. A fork is a speciation event where two finches on the Galapagos Islands suddenly diverge and never interbreed again. So they actually become two totally different entities. Similar kind of, if you use that metaphor, you can kind of apply it in this case, thinking that 9 and 10 have now become two separate entities that are so different that they can't merge back together. So this is what happens as we do software change management. T1 and T2 become things that we version, but the blue ones represent all the new features that we're adding, and the yellow line represents the official code base that we're going to consider releasing to the public. For those computer science people among us, it's interesting to think about the representation of what a code change tree like this might look like. This isn't a linked list, and it's not a linked list because there are branches in our software repository. It's not a tree, although I just said tree. It's not a tree because you can merge different branches together again. That makes it not a tree. It's not a directed graph because the way in which these changes happen over time prevent cycles from occurring within our data structure. And so it's more appropriately called a directed acyclical graph, or abbreviated as a DAG, and I've also heard it called a lattice as well. So it's just the representation of this for those who are following along at home. Finally, a few more terms. Clone means to copy an entire repository, and when you do that, you get the entire history of all the changes that have been made and by whom as well. Delta compression represents the fact that we're only going to actually keep separate copies of files that change. And we're only going to keep the smallest amount of information that we need to represent that change. So at each commit, we're not it appears the abstraction is that we're completely copying the code base. But the way the software change managements work is they only copy the very smallest amount necessary to keep the amount of hard drive space that you're using minimal. The process of tagging is the process of naming a particular snapshot, for example, giving it a versioning number. And then pushing and pulling is the process of synchronizing different repositories. For example, taking the repository on your local hard drive and synchronizing it with GitHub, or pulling from GitHub and synchronizing it with your local hard drive. So historically, how did we get here? Well, we've been progressing in our complexity and our ability to manage change. So about 1980, the tools RCS, which a revision control system, which has the programs CI, check-in, and CO, checkout, were made about 1980. It was okay, but it required a lot of discipline on the part of users. CVS was introduced in 1986 and Subversion around 2004. Git was introduced about 2005, and then GitHub came online about 2009, and since then has really exploded as becoming a major location for storing software on the internet. What is GitHub then? Well, GitHub is a web-hosted repository. It's a place where you can put these collections of software and all the changes that have been made to them. It's also a collaboration site. It's a place where you can go to have discussions about the software. It also has a set of forums that are attached to different commits within your changes so that you can have discussions about branches and commits and what you did in each one of those changes. It also has a built-in quality and security assurance system for doing continuous integration, for doing code quality checks, and for doing automated testing. If you would like to use a graphical user interface for Git, I recommend using SourceTree, a product by a company called Atlassian that, while very complex, makes using Git much simpler than it might otherwise be. What SourceTree enables you to do, among other things, is to connect your local hard drive repository to your remote repository, for example, one on GitHub. It allows you to mirror what's on GitHub on your computer. so that you can make changes on your computer and have them uploaded to GitHub automatically. This is a screenshot of what Atlassian's source tree looks like. And what you can see here is you can see my demo repository where I've been making changes to my web application as we've been going through these tutorials. And you can see the historical trajectory where the newest commits are located at the top. You can see that blue line with the circles in it. That represents the historical trajectory going from the past at the bottom to the present at the top. You can see that I've highlighted uncommitted changes. And by highlighting that, I'm showing which files have been changed, but which have not been snapshotted and put into my repository's history. By selecting committed changes, that causes index.html down on the bottom left to show up. And when I select and highlight index.html, over on the right, you can see the red and green lines, which show what's happened, what's changed to that file since the last commit. Once I have that index.html file located in my stage, indicated by the fact that it's right under the heading that says staged files, I'm now prepared to commit that file if I want to and create a snapshot at a new moment in time in which index.html and any other files that have changed, there's no other files that have changed in this screenshot, will be added to my repository. And once I do that, I can then synchronize it with GitHub by doing a push to GitHub. Right? So in the wild, these things get very complicated. So the Bitcoin software, the reference Bitcoin client, is an open source software. And you can look and see all the different collaborations that have happened within this software. So you can see that the history in this case, in this software, involves a lot of different branches. Many different people working on several different lines of code, each one of them represented by a different color on the history timeline on the left. Each one of the dots on the history timeline represent a different commit, but a different commit on different branches of the code. When the code separates out, going from bottom to top, that represents a branch, and when it comes back together, it represents a merge. So I've selected a particular commit on the purple timeline there, and by selecting it, I can see all the files that changed as part of that particular commit. You can see all of those yellow files that are on the bottom left corner have all been changed as part of that single commit. And when I highlight that first file, you can see the red over on the right. The red indicates the things that have been deleted from the previous commit, located one below. After making that commit, you can see that the next moment in time is a merge. It looks like merge number 10075, removed, unused, something. And at that moment in time, the blue is likely the trunk. And so at that moment in time, some developers' changes to the Bitcoin code were brought into the main trunk and made available to other people. So in the wild, or in real projects, this can get very, very complicated and requires a lot of social coordination around it as well. In our applications, we're going to keep it simple. And for the most part, I think we're just going to keep it as a linear progression, no branching. We're just going to use it as a backup mechanism. So as we move forward in time, we have the old code that was available to us if we ever want to go back to it. If you want to spend some more time studying this in greater depth, I recommend looking at the Wikipedia page on version control for a high-level overview of what version control is about. If you want to particularly learn more about GitHub, there are two good tutorials. One located on, if you want to know more about Git, there are two tutorials that I highly recommend. One is on GitHub. GitHub has a tutorial for using Git, and then Code Academy also has a tutorial for using Git as well. And that'll show you some of the details and complexity associated with the more advanced features of Git as well. So, in summary, Git is a tool that allows for software change management. Software change management, or Git in particular, helps developers manage changing collections of software source code, something that can be very difficult to manage, and you need a tool like Git, which itself is pretty complicated, in order to help keep control of it. GitHub is a web-based service that interfaces with Git to provide a common place to share source code repositories. And then finally, SourceTree is one of many GUIs that are available for interacting with Git, but it's one that is full-featured and very powerful. All right, very technical discussion of some of the source code management tools that we've got out there. Thank you for your attention.